Hey guys, Mr. Brown here, back with some more info from Chapter 6 from Klein's Organic Chemistry. In this video, we are going to focus on the content talking about nucleophiles and electrophiles in chemical compounds. And what we're trying to do, so we're going to move into discussing chemical reactions in the next little while now. And what this information is going to help us do is determine where reactions take place in molecules. Where are good places for things to happen in molecules? So we are going to talk about how most of the reactions we will study in organic chemistry, this is the 200 level, the introductory level. It goes beyond this for sure. We will do one chapter that goes against this trend, but other than that, all of the reactions that we study in the first year of organic chemistry are ionic reactions. Now, that may seem counterintuitive because we're not using ionic compounds for the most part. We're talking about organic compounds, which are mainly covalent compounds. But when we talk about ionic reactions, ions are formed. Usually an electron pair leaves an atom, leaving some charged species. That charged species can be a reactant, a product, or an intermediate. In our case, it is going to be mostly intermediates for our introductory reactions. But the important part is we'll generally see a charged species form somewhere along the way because we're taking electron pairs away and moving them around and forming bonds, not just one electron radical reactions, which, like I said, we will devote one chapter to, but that's not the core of the study of the first year of OChem. So moving on to the next point here, like I said, what we want to do with this information is try to figure out where reactions are going to happen, where molecules are going to trade those bonds, those pairs of electrons to bonds. And the first thing we want to be able to identify is where nucleophilic sites are in molecules. So nucleophile kind of really means nucleus loving. So what nucleophiles are pieces of molecules that want to find a positive site to bond to. So generally, nucleophiles are electron-rich environments. These are places where electrons are gathered and located in a molecule where we have a lot of negative charge that want to find a positive charge to bond to. These are Lewis bases in all respects, and we have some examples here that will show you. So these are all good examples of some strong nucleophiles. These are electron-rich environments and electron-rich moieties that want to find some positive place to bond to. One of the best nucleophiles is an oxygen atom that has a localized negative charge. So an oxygen atom with an extra lone pair missing a bond is obviously looking for somewhere positive to bond to. Notice the word localized there. It's especially strong when that lone pair is not experiencing any resonance. So in all of our examples that we see up there, none of those molecules, none of those lone pairs are able to resonate to other parts of the molecule. So it's a localized lone pair of electrons, a localized negative charge that really wants to find a bond to form. So those are all really good nucleophiles. We would call the whole species a nucleophile, by the way. Another one, or other examples, are your halide ions. So those are our real important ones: chloride, bromide, and iodide. So notice we kind of live off fluoride there. Fluoride's so super reactive. It's a little bit different from the other three. These really behave really well in organic reactions. So when we find these species by themselves, they're quite stable by themselves, but they are good nucleophiles, meaning if they can find some other positive place to park that charge, they definitely will. So our bare halide ions are very good nucleophiles as well. They're looking for a nucleus. And finally, kind of on the lower end of the scale, pi bonds themselves, we have those electrons kind of sticking up above and below the plane of the molecule. So those are electrons. They're bonded up already, but sometimes they'd rather be in a sigma bond than they would the pi bond, because sigma bonds are a little bit more stable. So if they can find a better sigma bond, pi bonds will do that. That's why we see pi bonds breaking in our molecules. Those can be areas of reaction in a molecule. So everything on this slide is an example of a good, strong nucleophile. Some electrons in search of a positive charge to bond to, or a positive site to bond to. So speaking of, if we can talk about nucleophiles, we can definitely talk about electrophiles, which is the opposite of that. These are positively charged sites in molecules, or sites in molecules that have some partial positive charge, and they're looking to bond that up with a pair of electrons that is looking for that nucleus. So we see an example here, methyl chloride, where we have chlorine replacing one of the hydrogens in a methane molecule. And we know from a lot of gen chem and organic chem now that that's going to be a polar molecule with that highly electronegative chlorine pulling a lot of the electron density toward himself and leaving a positive region of charge on that carbon. Note, the chlorine here in this case is not exactly what we would consider a strong nucleophile because it already has the bond. However, due to those inductive effects because of electronegativity, the carbon is really kind of exposed, and any sp3 carbon has its electrons being pulled, or any sp3 carbon bonded to a halogen has that same pattern where its electrons are being pulled from it. It's got an exposed part of its nucleus, and electrophiles can really seek that out and make a bond there by ejecting that chlorine, which is something we'll look at when we do our reactions. Some common electrophiles to look out for are, as I've already mentioned, sp3 carbons with bonds to hydrogen, whether that be iodine or chlorine or bromine. We have some examples here. So all of these carbons would share a positive partial charge because of the inductive effects of those halogens. Carbocations, carbons missing a bond altogether, I think it's pretty easy to see why that might be a good electrophile. They are looking hard for something to come in there, fill that empty orbital, fill that bond, and get that carbon back to octet rule status. So carbocations are great electrophiles. Finally, there's the carbonyl carbons, which we run into a lot, the carbon double bonded to an oxygen. There are a couple of different structures, ketones, aldehydes, esters, and possibly a few more, where we see a good electrophile activity at that spot. Due to the resonance structures, which we've already studied, we know that there's a resonance structure where we have a carbocation. So the resonance structure showing the carbocation there really clues us into the fact that that's a site, that carbon is a good site. It's not necessarily a carbocation. We know that it's somewhere in between these two. It probably favors this more than anything, but having that in the resonance structure means that carbon has quite a bit of positive character, meaning it can accommodate another bond if something comes along better than that double bond to the oxygen. So this is, all of our carbonyl carbons are good electrophiles as well. So that brings us to kind of the end. What do we hope to answer with these? And actually, here's a table that kind of summarizes everything. You can look that over and see what different structures might look like. I really suggest you really devote, even if you take 10 minutes and look at this and really make it mean something to yourself. If you can identify nucleophiles and electrophiles going forward without having to think really hard about it or go back and review notes, it will make your life a good deal easier. I have some examples here. So here we have some examples. We're going to try to figure out for the following molecules whether each of them represents an electrophile or a nucleophile. In the first case here, this is a methyl or like a propyl bromide, and so there's definitely some partial negative character here and some partial positive character here. So in this example, we would expect this to be an electrophile because we don't consider the bromine already bonded a nucleophile, even though he has some partial negative character. He's kind of happy in his position there. But the carbon really has, he's getting kind of bullied around, so he's got some partial positive character. If he can find a better bond than that bromine, he will. So we consider that an electrophile. In example B, this was a little bit harder to place. Our alcohols, they don't really do as much of a job as pulling any electrons from this carbon here. So this one's not really an electrophile. This carbon doesn't have a lot of positive characters, so it's not going to be an electrophile. However, the lone pairs on the oxygen, that's about the only place that we can talk about. So that one's would be considered a nucleophile. In this case, we do see some lone pairs on the oxygen, but more importantly here, because we have the carbonyl carbon with the partial positive character, that carbon is definitely going to be an electrophile much more than these lone pairs are going to be nucleophiles. In example D, the only structure we have that can be a nucleophile or an electrophile is the pi bond there. Everything else there, carbohydrons or hydrocarbons rather, are really stable bonds. And so that pi bond there, he might go search out a nucleus in order to bond to. So that one's going to be a nucleophile. Our good friend carbocation here really wants a pair of electrons to fill in that gap, some kind of bond. So that is an electrophile. Our localized electron pair on the oxygen there really wants to find a nucleus to bond to. So that's going to be a nucleophile. In the next few cases, notice we have those metal cations that we want to try to ignore. So if we put that in solution, what we get is a dissociation. So we get bromide ions, and those are great nucleophiles. Same thing here. When we put that in solution, what we get are hydroxide ions, which have localized negative charges on oxygen, so that's a great nucleophile. In example I, that's one of our methyl iodides, so that they've given us the structure there. We got a carbon, it's got a couple of hydrogens, and an iodine on it, so that's going to give that carbon partial positive character, meaning that this is going to be a good electrophile. And then finally, this weird looking formula down here where it says KOC, so that's literally a potassium ion. So what this looks like is a potassium ion with CH3, CH3, CH3. So that is what we consider potassium tert butoxide. So this is just a stabilized version of one of these oxygens. It's an ionic version of one of these oxygens with a lone pair that is not bonded and a localized negative charge on that oxygen. So that is going to be a good nucleophile as well. And so, I don't know if that is going to be an electrophile. That carbon is looking for a bond if he can find it. In the last question there, it says the following compound can react with itself because it has both a nucleophilic center and an electrophilic center. Identify the nucleophilic center and the electrophilic center in this molecule. So we know that sp3 carbons that are bonded to halogens have a little bit of partial character. So that's going to be our electrophilic center. And that is going to make the lone pairs on the oxygen there be our nucleophilic center. So that's some examples of identifying nucleophilic sites and electrophilic sites in molecules. And as I mentioned earlier, if you can do that kind of quickly without having to refer back to the notes, that'll make your life easier going forward. As always, if you have any questions, email me, let me know what you think, and thanks for watching.